start with kind of a random conversation here. If I said to you, give me a sequence of numbers, what would you say? What would be a sequence of numbers that would you like to? What?
1, 2, 3, 4, 5.
Okay, that's too easy. That must be a little more creative than that. That is a sequence of numbers.
2,
What?
so I'm not 6.
What?
2, 4, 6.
2, 4, 6, 8. Okay, so that's a nice sequence of numbers. Okay, can anybody give me another sequence of numbers? We're just gonna look at different ones.
100, 1,000, 10,000, 100,000, million.
Okay, 100, 1,000,
We can start with 1 if you want.
all right?
3, 9, 27,
Okay,
1.
these are all, actually, that one's kind of like this one right here. I'll use yours because it's smaller numbers. 3, 9, 27. So what do these two have in common? That's different than that one. What's these two, how are we doing this? How are we getting from term to term in these two? We're multiplying by the same number, okay? Would everybody agree with that? So in this one, it looks like we're multiplying by 100. And in this one, we are multiplying by 3. When you get from term to term, by multiplying by the same number, the sequence is called geometric. Did you guys do these last year? And a geometric sequence, we just got done saying, is generated by multiplying by the same number. That number is called the common ratio. And for this sequence, the common ratio is 3, because that's what we keep multiplying by. And for this one, the common ratio is 100, because that's what we keep multiplying by. Right? Now, that one is not geometric. That's a sequence, you definitely see the pattern, but how are we getting from term to term in that one? We're adding 2. When you get from term to term by adding, the sequence is called arithmetic. And the number that you keep adding is called the common difference. Now, these words, common ratio and common difference, oh, so for this one, the common difference is 2. That's the number we keep adding. Those terms should make sense to you. Look, what's the ratio of 9 over 3? What's 9 over 3? What's 27 over 9? See why it's a common ratio? It's always the same number. And here, 4 minus 2, 6 minus 4, 8 minus 6. It's always a common difference. Okay? So, part of this lesson is to figure out and use formulas that allow us to find terms of the sequence without writing them all out. Clearly, Joe Funk, if I said to you, find the 1,000th term of this sequence, you could just keep adding 2, right? We want to come up with a way to make it a little less tedious than that, all right? So I'm gonna put a different sequence up here. We're gonna get to the notes in a second, but I think he left out some kind of important things. So I'm adding to it a little bit. Let's say we have the sequence 4, 7, 10.
We have like the sequence.
Okay, just hang on, I'm looking at this one right now. Arithmetic or geometric? Arithmetic, why? Getting from term to term by adding 3. So the common difference is 3. Now I want you to look at this, guys, because we need to do something besides memorize. We need to understand what's happening so that we can start tying arithmetic sequences to linear functions and geometric sequences to exponential functions. But we have to understand what's going on in order to do that. So, the very first term of the sequence, and I use a sub 1 as my notation. The notation you use is irrelevant. A sub 1 indicates the first term. So what do you think A sub 2 indicates? Okay, you got it. A sub n will indicate the nth term, right? Whatever you want n to be. The first term of our sequence is 4. The second term of our sequence is 4 plus 3. The third term of our sequence is 4 plus 3 plus another 3. So we have our first term, which is just 4, plus no 3s. We didn't add any 3s, so that's just 4. This one is 4 plus 1 3. This one is 4 plus 2 3s. What do you think the fourth term is going to be? 4 plus 3 3s? Okay, so we see a pattern, definitely a pattern. What do you think the nth term is going to be? 4 plus n minus 1 3s. Did you notice that the number of 3s is 1 less than the term you're finding? If we're using this formula or this strategy, okay? In general, the nth term of an arithmetic sequence is going to be the first term. In our case it was 4, but it would be whatever the first term was, plus the common difference times n minus 1. So 4 was our first term, 3 is our common difference, n minus 1. So if we wanted, in this sequence, if we wanted the 50th term, we could calculate it in a snap. The 50th term will be 4 plus 3 times 49. Does that make sense to everybody? I just work it out and I'm done. Okay? This is the formula that you used last year, and it will always work. It isn't always the formula that he uses in the notes, and that's okay, it doesn't matter. Use whatever formula you're comfortable with, but this is the one you used last year. Okay? Now, we're doing the same thing with geometric sequences. So this is for arithmetic. This is arithmetic. Let's look at a geometric sequence. Geometric sequence, let's think of something a little bit different. How about 3, 6, 12, 24? Is that geometric? If it is, it has a common ratio. What's its common ratio? 2 times 6, the ratio is 2. So the first term is 3. Now you're gonna see in the notes that sometimes he'll say G sub 1. Does that matter? Is that gonna confuse us? No. First term is 3. Second term is 3 times 2. Third term is 3 times 2 times another 2, which could be written as 3 times 2 squared. The fourth term is all that, 3 times 2 times 2 times another 2, or 3 times 2 cubed. Are you starting to see the pattern there? So what's our formula, do you think, gonna be for a geometric sequence? Well, it looks like we take, in this problem, 3, but what was 3? 3 was our first term, times 2, which was our ratio, and then what power, if this is an n, then that power would be n minus 1. So in general, we're gonna take our first term, we're gonna multiply by the ratio to the n minus first power. And that's gonna be your geometric, formula, one of them. All right? Okay. Okay, all right. So, I just wanna talk about this, and I just have to, talk about this. It's so cool, it's been years and I remember that I taught Daniel's mom back in the day. Wonderful, wonderful student, one of the smartest kids I ever taught. This is a true story, now you must listen to this, because it's amazing, and you may have already heard it, but I'm not from me, but from someone. So Kathy came into class one day, and she said, Mrs. Ford, my dad and I were watching TV last night, and they said something on TV, I was one of those science shows or something, and they said something on TV that can't possibly be right. And my dad thought maybe we could talk about it in math class. And I said, okay. I said, what is it? They said on TV that if you took a standard checkerboard, you know what I'm talking about, like you play chess, checkers and chess on, and you put one checker on the first square, 2 on the second, 4 on the next one, 8 on the next one, and so on. Stacking your 1 checker, 2 checkers, 4, and so on. By the time you got to the last square on the checkerboard, there would be enough checkers stacked up to reach the nearest star. And she's like, the nearest star is the sun, and the sun is 9.3 times 10 to the 7th, 93 million miles away. Right? She said, no way, how can that possibly be? Well, we can figure this out, because what kind of a sequence is this? Geometric. And all geometric sequences are going to conform to this pattern. All right, how many squares are there on a checkerboard? 64. So aren't we really wondering how many checkers there are on that 64th square? So we'll take our first term, which is 1, and our ratio, which is 2, to the 63rd power. All right, so let's take our calculators out. Now let's just figure out what 2 to the 63rd is. Now remember, you gotta look all the way across, because you gotta notice that E on the end of it. So we've got 9.2 something times 10 to the 18. That's a very big number. But what does that represent? That number represents the number of checkers. That isn't necessarily a distance, right? So we gotta agree on, okay, so here's, I don't know, here's about an inch. How many checkers do you think I can stack on top of each other? 4? 3? 4? 2? 3, can we just say 3?
3.
All right, so I'm gonna divide this number by 3, and that's gonna give me the number of inches then. So then I'm gonna divide it by 12, and that will give me the number of feet. And then I'll divide by 5,280, and that will give me the number of miles. 4.85 times 10 to the 13th miles. So that is way more than to the sun. Isn't that amazing? You're incredulous, aren't you? But it's absolutely true. It's incredible. I want you to think back. Exponentials look like this. When you keep doubling, when you keep multiplying by any number bigger than 1, when you keep multiplying by it, these things just get absolutely gigantic. Isn't that amazing? I'll never forget that story. It just was, I go, wow. So then, I always gotta share this story too. Some of you are gonna be teachers, I hope, some of you are gonna be teachers, and you're gonna figure out that the first year is absolute hell. I am not kidding you. The first year is hard for everyone, terrible, no lie, I'm not lying one bit. I spent almost every afternoon my first year in the faculty lounge sobbing. It was awful. First year's just awful. You just hope to survive it. Anyway, I had this kid, great kid. As a new teacher, first year teacher, you get whatever's left over. When they do the scheduling, you get whatever's left. So I had a first year algebra class. In those days, there was a 2-year math requirement. You had to pass pre-algebra and algebra 1. That was what you had to pass back in those days. I taught this low algebra 1 class. I had one senior in this class. Algebra 1. I had a bunch of juniors, sophomores, and a few freshmen in this class. 36 of them. 36. Brand new teacher. No idea what I'm doing. I know the math, but I know nothing else. And okay, so I have this kid, and he's constantly causing trouble. Well, I was brand new. I came from a farm school. So at the time, my punishment was, you're not paying attention? Give me some push-ups right now. Well, this kid was a wrestler, a very good wrestler. And we have a strong tradition of wrestling here. He's a very good wrestler. And he got to the point where he was doing his one-handed push-ups. He was putting his feet up on the ledge. He was getting in trouble on purpose so that he could show off his push-ups. So, I had it. I did. It's kind of mean what I did, but here's what I did. I had his mom come in, had him come in. At the time, we had a female dean of students, and I sat down with those people, and I said, okay, here's the deal. You need to come to school, all right? He was not the senior, he was a sophomore at the time. You need to come to school. I need you to pay attention in class and behave yourself. Just come to school and be quiet. You don't have to do anything except just be quiet. As long as you can do this for me. Starting tomorrow, you're going to stay after school and you're going to do 1 push-up. The next day, you're going to stay after school and you're going to do 2 push-ups. The next day, you're going to do 4. The next day, you're going to do 8. We wrote this down. This was like an old contract. And I said, as long as you can keep doing that, come to class. You don't have to take a test. You're going to get an A. I'm going to give you an A. You don't have to take a test. You don't have to do anything. No homework, no nothing. Just be in class, keep your mouth shut, and after school, do your push-ups. Well, I'll never forget the dean looking at me saying, are you sure you want to do this? And I'm like, yeah, because what did I know? Because I'm a math teacher. He was not going to be able to keep that up very long. What's 2 to the 8th? On the 9th day, he's already doing, 256 push-ups after school? And then the next day, he's doing 512 push-ups after school. So it didn't take very long. And to his credit, he was good as gold the rest of the year. He did what he was supposed to do, passed, everything was great. To this day, when I run into him, and I run into him periodically, he says, hey Sarge, he calls me Sarge. But we ended up friends, not at the beginning, but at the end.
What's his name?
I'm not telling you what his name is.
I guess.
No. I mean, you can guess, but I'm not going to tell you if you're right or wrong. I don't think you guys, I don't know if you guys would even, you would recognize probably the name, but I don't think you've ever met him. All right, so let's get back to our notes now. Story time's over. The big deal of today is 2 kinds of sequences, arithmetic and geometric. Our job is to recognize them and find certain terms of them. All right, so here we go. A sequence is a function that maps the whole numbers onto the real numbers. Mrs. Ford, what in the world does that mean? Well, I want you to think about like what we just talked about. Here's a sequence. notes, guys. A sequence is a function that maps the whole numbers onto the real numbers. Here's the deal. The first term is 3, so that could be written as an ordered pair. It could be. And if I'm going to sketch it, I'm going to need what?
I just didn't get one of those.
Well, they were handed out a long time ago. Did you look in your thing? Okay. So the first term is 3. The second term is 4. The third term is 5, and so on. So do you understand how a sequence could be represented as a function? And the domain of the function is the whole numbers. Sometimes we talk about a sub 0, a sub naught, that's called, and that means the original number. Now, I prefer to think of it as a sub 1, but it's the same thing if you think of it as a sub 0. Changes your formula a little bit, and that's okay, but you can have a starting number, a sub 0. In this case, I'm just using my first term is 3, second term is 4, and so on. So, these numbers must be whole numbers. Would you agree with that? You cannot have the 1.5 term. It has to be a first term, second term, third term. But these numbers could be anything, couldn't they? Couldn't I have a sequence made up of fractions or radicals, whatever? Sure. So that's what we mean when we say the domain is the wholes and the range is the reals. Okay. All right, next. This means we're, okay. When we graph a sequence, okay, so if I want to graph this, I have the point 1, 3, 2, 4. Oh my goodness. What's going on there? What shape is that? That's a line. An arithmetic sequence, because it is going up by the same amount every time, has a constant rate of change. An arithmetic sequence is going to be linear. However, when you graph a sequence, it is just the dots. Do not connect the dots, because if you connected them, then wouldn't you be including this point? And that point is 1.5 comma something, which is not allowed. So when you plot your sequence, the arithmetic will be linear. Dot. Don't connect them. Okay? All right. So consider this sequence. He's just made up this sequence for you. And he says, find a sub 1. Okay, that's easy. What's a sub 1? 1. And find a sub 7. What's that?
24. Wait, no, 25.
25? Who said 16? No, I don't want to think about how you got 16. Plug 7 in here. 4 times 7. All right. Now, he gave you some formulas in there. I have given you the formula from your past. I don't care what formulas you use. You are responsible for knowing a formula for arithmetic sequences. You can use his options. You can use the option I put up on the board. I don't care. You only need one. You only need one. Learn one. Whatever one works for you. Okay? Now we're going to sketch a sequence. That's what we're doing in the example there. We're going to sketch this. So a sub n equals 3n plus 1. Okay. Now we're allowed to put in 0. So if we put in 0, we would get 1. There's no way we're going to be able to graph every point of this sequence, right? I mean, you're not going to be able to plot the whole thing. So if you want to start with 0, that's fine. If you want to start with 1, that's fine. What do we get when we put in 1? 4. And we'll put in 2 and get 7. Let's talk about this for a minute. Is this arithmetic? What shape am I getting? A line? And what do you notice about the slope of that line? The slope of the line is actually the common difference, isn't it? Aren't we going up 3 and over 1 each time? So your common difference is the slope. Y equals mx plus b. Yeah, all the pieces are coming together. Example 2, for each of the following, determine if it's arithmetic. What do you think about A? Well, my absolute gut feeling is no way, Jose, because it's got a squared in it.
Yeah.
But if I'm not sure, and I really don't know, what could I do to check?
Throw a few numbers.
Put in 1. Yeah, if you put in 1, you get -2, right? What do you get if you put in 2? 1. And what do you get if you put in 3?
6.
Okay, that's enough. Because if it's arithmetic, doesn't the distance from here to here have to be the same as from here to here? And it's not. So no, that's not arithmetic. What about B? My gut feeling is yeah, and the common difference is -6. But we can check some points. We put in 1, we get 4. If we put in, oh no, not -2. The common difference is -2. If I put in 1, I get 4. If I put in 2, I get 2. If I put in 3, I get 0. If I put in 4, I get -2. Is that arithmetic? Yep, with a common difference of -2. Slope is -2. All right, what about C? That's just all written out there. Yeah? Common difference is 5. All right, what about D?
No.
No. Now, you gotta be careful. Do you see a pattern? Is there a definite pattern in this problem? Yes, there is. But that wasn't the question. The question was, is it arithmetic? And it is not, because we're not getting from term to term the same way. Agreed? Okay. Number 3. We have an arithmetic sequence, so they're telling me it's arithmetic. They're telling me the third term is 8, and the common difference is -3. And I have to find a formula, a rule, for a sub n, and find a sub 12. Now, there's lots of ways to do this. I have memorized and used this formula for my arithmetic sequences. Is what we use in this hallway to be consistent. If I want to find a sub n using this formula, what do I need to figure out? What my first term is? Now, what did they tell me? They told me that my third term is 8. So if I think about this, this is what my sequence looks like, right? Now, what does this mean? If the common difference is -3, that means to get from here to here, I'm going to add -3. But if I really want to know where I started, I wouldn't be adding -3 I'm adding -3 going that way. But if I'm going to go this way, I am just going to add 3. Does that make sense to you?
Yeah.
That this number would have been an 11, and this one is a 14. So my formula will be 14 minus 3 times n minus 1. First term plus common difference times n minus 1. which is 14 minus 3n plus 3. So my simplified formula is 17 minus 3n. Now, have I lost anybody? Remember, there's other ways to do it. Ultimately, we're all gonna end up with the same 12th term. So what do I do if I want the 12th term now? I'm just going to plug in 12, and it looks like negative 19. Is that okay with everybody? All right, now I have another arithmetic sequence. But this time, I know the second term is 7, and the 6th term is 9. And I want to find my formula again, and then eventually I want to find the 24th term. So who has an idea here? There's a lot of ways we could be creative with this problem. Does anybody have an idea? Yeah, Emily?
Would you like subtract 7 from 9 and then divide it by 4 since there's a difference of 4?
Okay, now wait a second. Emily says, let's kind of just look at this for a second. So here's your second term. There's the 3rd, 4th, 5th, and 6th. Now what Emily is saying is, if this is arithmetic, then isn't each step I take going to be the same size? And there's 1, 2, 3, 4 steps being taken to get from 2 to 6. So she said if the total distance covered is 2, 7 to 9, but it's taking me 4 steps to get there, then each step is going to be how big? Half. So my common difference is a half. All right. So now, very good, Emily. Does that make sense to everybody? Okay, that's good. All right. Now what? By the way, that strategy will not work unless the sequence is arithmetic, right? Okay. All right. What now? I still need a formula, and I need a 24th term. What?
On your first term.
So my first term, remember, that's the second. So the first term would be 6.5, 6.5. So my formula will be 6.5 plus 0.5 times n minus 1. Does that make sense to everybody? So 6.5 plus 0.5n minus 0.5. I have 6 plus 1/2 n. Does that make sense? Did I do that right? So now if I want the 24th term, looks like the 24th term will be 18. Does that make sense? Good job, good job. All right, number 5. Several terms of an arithmetic sequence are shown above. Okay, so this time instead of giving you information, they drew a picture of it. Could you tell without being told that it's arithmetic? Yes, because it is linear. Yep. So the terms are 8. The terms are 8. What's my next term? 6. The next one's 4 and 2 and so on. What is my common difference?
-2.
-2, which is the same as the slope of the line. Find an expression for a sub n and find the 17th term. So what do you think, Mr. Brady?
You gotta find the first term, which is, alright, we already have that. And then, just set up the equation, 8 minus 2,
Well, for the
17 minus
formula,
1.
well, it's going to be that, but we want the formula first, so we have to leave an N in it. Okay, we need to talk about this here, just hang on, we need to talk about this, make sure this does what we need it to do. So, A sub N is gonna be 8 minus 2N plus 2. Did you get 10 minus 2N? Now, I just wanna make sure that it fits everything. According to this formula, what would A sub 1 be? Okay, see, this is where we gotta be really careful, because A sub 1 is not 8. Look at your graph. What's 8? A sub 0, right? So, I need you all to understand that A sub 0 is 8, right? Which is totally fine. You can include it in the sequence. But when you use this formula right here, what has to be in that spot? A sub 1. So that has to be the point that is connected to the x value of 1. Does that make sense to you? So I don't think I want an 8 here, do I? What do I want here? A 6. And then I have an 8 here. And now does my formula generate the points it's supposed to? Yeah, if you put a 0 in here, if you put a 0 in, you get 8. Is that what you're supposed to get? 0, 8. So when you have your picture, make sure that your points from your picture are aligning to the formula that you are building. Okay, and then the 17th term will be 8 minus 34, which is what, negative 26? Is that right? And that's it. Is that okay? Oh, looking full of vim and vigor there. All right, are we okay with that? All right, let's turn the page. Let's turn the page, and now we're going to talk about geometric sequences. So again, I have provided you with a formula consistent with what you already know. He has provided you with a couple of alternatives. It's completely up to you. You need one formula to answer these questions. So you pick the one you want, and then make sure you're putting the right numbers into the spots. Okay. How do we know if a sequence is geometric? You get from term to term by multiplying, right? So let's take a look at this one. He says g of n equals 8 times 1/2 to the n. We are going to draw a picture of this. So if we put in 0, what do we get?
4. Right now it's 1, so it's 8.
8. As you remember, anything to the 0 power is 1. We'll have a conversation about that another day. All right, let's put in 1. What do I get if I put in 1? 4. If I put in 2. Okay, so just from the points I plotted, even if they didn't tell you it wasn't arithmetic, would you recognize it's not? Yeah. All right, so put in 3 and it's 1. And I put in 4 and it's 1/2. Oh my gosh, you see what's going on there? What's happening with these terms? They're getting smaller and smaller. Remember the checker problem? Those terms were getting bigger because we kept multiplying by 2. These guys keep getting smaller because we're multiplying by 1/2. That common ratio matters. If the ratio is bigger than 1, you are exploding. If it's less than 1, you are shrinking. Okay, everybody good with that picture? All right, remember, we don't connect the dots. We just have dots. All right, for each of the following, determine if it could be geometric. If it is, give the common ratio. All right, let's talk about 3n squared. What are some terms of 3n squared? What would the first term be? Second term? Well, one more, third term? Not 28, not 48. 3 squared is 9 times 3 is 27. Now, that's enough to answer the question. Would you agree? Because if it's geometric, whatever I times here, 4, is what I would have to times here. Geometric means the ratio, the ratio is the same. And 12 over 3 is not the same as 27 over 12. That is not geometric. All right, what about the next one? Sure looks like it. That's my formula. Does this thing fit that formula? So I believe this one's geometric. What's the first term? 4. What's the common ratio? 2. Now you can work them out if you want, but since it fits the formula exactly, it's geometric. Does that make sense to you? All right, how about the next one? What in the world is happening here? What's your thought on C? Not geometric. Now again, can you predict what's going to come next? Yeah, you can figure this out, but there is no common ratio. If we looked at every other term, then it would be geometric. But when we look at the whole thing combined, it is not. That's a no. How about D? Yep, and the common ratio is? Negative 1/2. When your common ratio is negative, your terms are going to flip back and forth between positive and negative. All right, example 7. I know the first term is 12. And I know my ratio is 2. And I want to find a formula. Oh, that's a no-brainer. The formula is going to be what? 12? Oh, wait. That's the first term is 12. First term is 12. So 12 times 2 to the n minus first. There you go. There's your formula. That was easy. And then what's G sub 4? Well, 12 times 2 cubed. 96, I think I'll go with 96. Third time's the charm. Several terms in a geometric sequence are shown above. Find, I'm on example 8 now. Find an expression for g of n and use the expression to find g sub k. Alright, so let's look at some terms here. It looks like the first term, if we let n or x be 1, the first term is 4. The second term is 2. The third term is 1. Is what I'm doing making sense to you? Okay, so what's a formula? I think I have enough to write my formula. My first term is 4.
Times 1/2.
How am I getting from term to term here? What am I doing? Timesing by 1/2. There's my formula. So if I want the 10th term, I need help on that. 1 over 128 maybe? check that. Is that okay? Everybody okay with that? All right, so let's take a look. There's a couple things in this next paper. It's called the number of goals. I'm not sure what that means, but I want to talk about a couple of these questions. So read the problem about her jogging every day. And let's look at some of these. So we've got the first day of July, she does 15 minutes. And then it tells me in the problem that every day she adds 5 minutes. So this would be 20, and this would be 25, and so on. And they did the last one for me. Yeah, the last day, it was 165. Is this arithmetic or geometric? Yeah, which one? Arithmetic, because it's going up every day by the same amount. We're not multiplying, we're simply adding 5. So the common difference is 5. Write a rule that gives the amount of time that Mallory runs on the nth day. So in other words, A sub n would be what for this set of information? A sub n is going to equal, here's your formula, or a formula. You may choose to use one of his, and that's fine. Our answer will be the same. So A sub n is going to equal your first term, which is 15, plus your common difference, which is what we keep adding by, which is 5. So when we simplify that, 10 plus 5n, is that what you got? And then it says show that it works. Oh, yep.
Do you have to simplify it, or can you just leave it?
When you write the rule, it should be simplified. And even though that seems, I know, goofy, keep in mind we're making a connection between arithmetic sequences and lines. So this is y equals mx plus b. So we're trying to keep it all the same. All right, now show that it works. What can I do to show that it works?
Plug in.
Let's try it. Let's see. It doesn't give me 165. So A sub 31 is 10 plus 150. Uh-oh.
That's right.
Oh, 31, 31. That's 155. Now, oh, gee, I was doing the wrong thing. Yeah. Are you okay with that? Now that I fix that? Okay, so it does work. Now, it's number 3 and 4 that I want to talk about. Number 3 says, what was her average run length during the month of July? Now, how do I find an average? Add them all up and divide by however many there are, right? So is an option to finish the table, add all these up, and divide by 31. Is that an option?
Yeah.
Okay, I do not want that option. I could do it, I don't want to because it's tedious. Do you have another thought? Sandra?
Can you just find the median?
Now, the median is different than the mean, right? I mean, in general, what's the median? The median is the number right in the middle. So for this set of data, the one right in the middle would be 16, wouldn't it? And the 16th term is 90, I think. Now, the question didn't say find the median, the question said find the average. But in an arithmetic set of numbers, aren't they the same thing?
Yes.
Because think about it, aren't all of these gonna be less than 90? But these are all gonna be the same amount, bigger than 90? So does it make sense to you that when I add these up and divide, it's gonna come out to be 90? Very good, Xander, very good. Very good thinking. Now, again, arithmetic sequences are so special. That would not be the case in another set of numbers, but in an arithmetic set, it is. Good work. And finally, number 4, how many minutes total did she run in the entire month of July? Explain your strategy. So again, one option would be to take all of these and add them up. Wait, didn't you just tell me that if I added all these up and divided by 31, I'd get 90?
Did say that.
Isn't that what you just got done telling me? So what would they have to be all added up? 90 times 31? So those of you that are like thinking, oh my gosh, remember, there's a meat and potatoes way to do this problem, and that is figure all these out. And then average them up or add them up or whatever you want to do. But with arithmetic sequences, there's always a back door that can save you some time. Okay? All right. Well, we'll talk more about this. I want to get you going on your homework though. So I'm going to pass out your homework.